May we have your attention, please?
The RSSB managed research, development and innovation program has given rise to a good number of computer-based models, any of which has the potential to bring benefit to the railway. But, as leading health and safety on Britain's railway makes clear, the path to some of the best improvements lies in collaboration. But the intellectual property of many of those models lies with commercial organisations, which raises the question of how one company can share the benefits of its models with another without revealing its source code, its expertise, and its specialist knowledge. One possible solution is FMI, or the Functional Mock-up Interface. This is a tool that, as best I understand it, allows models to talk to each other. It allows them to exchange or share data outputs without giving away how they actually worked up those outputs. So neither party has to give away its secrets, and both can benefit from even richer information that's generated by collaborating. RSSB's R&D program has already explored the applicability of this approach to rail recently, and so I have with me today David Golightly and Ken Pierce, both from Newcastle University, who will explain things more clearly. Today we're going to talk about the work that they've been doing with FMI and the potential that they see for the rail industry. David and Ken, welcome both to the RSSB podcast. Could I ask you to introduce yourselves and tell us how you came to be working with the railway? David, would you go first, please?
Hi there. Yes, my name's Dave Golightly. I'm a lecturer in Human Systems Integration at Newcastle University in the School of Engineering. I've been working in human factors applications for the railways for probably just over 15 years now, initially starting in signalling, but also looking at things such as driver performance and passenger experience. And that's how I got involved with leading the RSSB-funded DECIDE project on FMI, which we'll be talking about today.
Thank you very much, David. And now, Ken, please.
Hi there. So my name is Ken Pierce, and I'm a lecturer in cyber-physical systems, and I'm in the School of Computing at Newcastle University. And my work is on modelling and simulation, and in particular, collaborative modelling and simulation. So how we can make use of all the really good work being done, but often in little pockets, and working on ways that we can help bring these together. I got involved in rail. David and his colleague Roberto Palacine invited me down for a coffee, and then we had a chat, and they said, we've got this really interesting area where we think your work on FMI could help. And that's how we got started on the DECIDE project.
Thank you, Ken. So we have two very different perspectives on the topic of modelling and collaboration. I feel this is going to be an interesting conversation. Ken, you're the computer specialist. Would you explain, in as plain language as you can, what functional mock-up interface means and how it works?
Of course. So I'll try my best to keep it simple and understandable. So as I mentioned before, I work with modeling. A model is generally something that is a computer program or similar that can tell us something about a system or component. So we can ask it some questions. So that might be what we call static analysis, so just working out if the connections all work together, or dynamic analysis, so we can do a simulation and see how something evolves over time. Now, often when we get to more complicated or complex systems, such as the railway, there are lots of individual parts that have to work together in order to see the behavior of the railway. So we've got the rolling stock moving around, we've got driver behavior, we've got passenger behavior, weather. These can all come together. Individually, there is a lot of expertise in how to model these aspects. So models of weather, that's how weather forecasts work, models of rolling stock and how those work on, let's say, cases of low rail adhesion. But these are often very siloed. So you've got, as we mentioned before, one company working with its own model of one aspect of a system, and another completely different company with expertise in a different model. Now, in order to see these system level behaviors, so how a timetable interacts with driver and passenger behavior, for example, we really need these models to work together. Now, we can either try and come up with a brand new modeling language that can capture all of these aspects, but it's, I would say, impossible to do that. So this is where the functional mock-up interface comes in. And instead of trying to build a brand new thing, we try and connect these existing models. So we have a passenger model talking to a train model, talking to a timetable model. And really all the functional mock-up interface does is provide a standard way to provide what we call a wrapper around a model, which describes what's in the model, what are the inputs and outputs. And then because that's in a standard form, we're able to connect those models together and run, in this case, what we would call a co-simulation. So we're then able to do what we call collaborative modeling. So by plugging the models together, we can really connect not just the models, but the expertise and the innovations that are going on in all these separate areas. And often we found that by connecting the models, we're also able to connect the people and use it almost as a shared language that help us move towards working together. So I might not know too much about human performance, but if we can capture that in a model, then we can connect that with models that I know about, let's say on train control, which would be more my area as a computer scientist.
Thank you, Ken. It sounds like it's a very complex system that you've described relatively simply. It's a good thing we've got some experts working on this. RSSB has done some work recently on the potential value of opening up data sources and sharing, and it found quite a few barriers and challenges. Can you tell our listeners how the FMI approach would overcome some of those?
Yeah, so as I mentioned, FMI is really a tool for collaboration. The benefit of this FMI wrapper means that you don't actually have to share the nuts and bolts of your model necessarily with another company. So one thing we found is generally if you create a model or a tool that can produce models, that's your bread and butter. Your company is making money off that. So if you feel you're giving away that IP, then if you give away too much, then there's no need for someone to come back to you and continue that customer-supplier relationship. Now, using FMI, when we produce these wrappers, what we create are called FMUs, so functional mockup units. So each functional mockup unit is some model with some inputs and outputs that we can run in a co-simulation. But actually, it's possible to hide the internals there so that even if someone has that copy of their model, they really can't get inside and see more than just the inputs and outputs, which gives companies much more confidence to be able to relax some of their maybe hesitancy about giving away knowledge and secrets for the benefit of the overall system, so they can still maintain their intellectual property. They can also connect that aspect of the system into the greater system model, and then the overall benefits are felt across. Some of the other challenges involved with data sources and sharing are what we would call legacy models. So often work is done to produce a model, and if this works well, then it often keeps getting used. And then people move on, technology moves on, but some of the models that are used, particularly in rail, have been there for quite a while, and now they only run on one specific older computer, for example. So instead of trying to work out how that model works, someone coming in and saying, how did the person write this? We can simply wrap that model as an FMU, and then an old model is then able to talk to, let's say, much newer models as well. And that's another way that FMI can help there.
Thank you, Ken. That's very clear and obviously has some interesting potential. Having said that, you've already proven the feasibility of using FMI as part of an RSSB research competition on the topic of decarbonisation. David, would you tell us something about how FMI was used in that work?
Sure. So, decarbonisation, we thought, was a really good example of a problem where FMI could be brought to bear. So decarbonisation is a classic example of a systems problem. You might get various components or subsystems to work in an energy efficient manner, but when you plug them all together, you may find some additional sort of cumulative benefits, or indeed sometimes things start to interact with each other. A really great example of that is people come up with driver advisory systems that are more energy efficient, but do they work well within the constraints of a real timetable? Something like that. So decarbonisation is a problem where you really need to think about the components and how they work together. A lot of those components have models associated with them, but the challenge is to get those models to talk together so you get an overall view of power performance. So essentially the side project was looking at a collaborative environment where you could test out decarbonisation solutions. That feasibility project involved 3 tasks or work packages. First was to build a small test FMI model or FMI implementation, I should say, where we took 4 or 5 different models. One represented power supply, one represented rolling stock, one represented what we call the movement authority, or if you like, the signaling system and the track, and one represented the driver. And we plugged them all together, and we were able to try out different configurations of, say, different types of driver performance or different types of light weighting. We also had a regenerative braking system, and we could see how those different combinations of elements would impact overall energy performance for our little test model. Importantly, we had 2 trains. So what you can do is you can start to see how the performance of one train impacts the performance of the train running behind it. So again, it might be more energy efficient, but actually what you find is it's harder to keep both trains to the timetable. Second part of the activity was to think about how you might scale this up so it operates on the cloud. So this would allow suppliers who are currently outside of rail to contribute their simulation models, and you can essentially plug and play simulation models and try out different combinations before you make a commitment to wholesale system development. Then the third task was just to work with the rail industry and understand what the appetite for this was, understand what sort of models were available that might be amenable to FMI. What we found was there were very few models that were amenable to FMI, but a lot are delivered in a format that could be easily converted into FMI. So we see that there's sort of considerable opportunity here. There's a technical feasibility, but there's also use cases and existing models that could be used with FMI to support decarbonisation.
Thank you, Dave. I know from our discussions when planning this episode that you have some more ideas about how FMI could possibly be applied to other areas of great value to rail. Would you like to expand on that?
Sure. I mean, the decarbonisation is a systems problem, but a lot of the problems we face in the railways are systems problems. They're about the integration of multiple technical, human and operational elements all trying to work together in harmony. So there's a number of situations where one might take individual simulation models and try and use them together in harmony to model systems effects. So an obvious one there is kind of operational performance. What happens if you start changing the configuration of signals, timetable, change driver performance behaviors? What are the kind of impacts you might see there? Another thing might be adhesion. There's a lot of simulation work in adhesion. But what I'm interested in is, well, could we build standalone driver performance models and plug them into the adhesion model to trial out different conditions? And I guess a final area would be, I mean, we're talking about, the physical running of the railway, if you like, but actually FMI as an approach can be applied to anything. So what happens if you would have, say, models of, I don't know, the logistics movements associated with moving concrete to and from a large rail civils construction site? What happens if you've got simulation models of the generation of that concrete? We know that the generation, movement and use of concrete is one of the biggest contributors to CO2. Can we use simulation models in that context to try and optimize performance? And that gives us a different type of decarbonisation benefit.
Thank you, Dave. Those are some examples of where FMI could be used for the benefit of the railway, but it's been around since 2010 or thereabouts, and you've been working on it for a number of years. Could you talk to us about an example from another industry where what might have been seen as unusual collaborators have worked together to deliver extraordinary or unexpected results?
I think I could probably have a go at this one. So, as you mentioned, FMI kind of came out in the 2010s from the automotive industry. So there you have well-defined supply chains dominated by sort of 5 or 6 very large key manufacturers. So really it's, if the people at the top say follow FMI, then that will trickle down all the way down, and then they really see the benefit of that. So there you might have, because the supply chains are so long, essentially, even if you're working for one of those big automotive companies, you might be quite far down the supply chain in terms of testing, for example. So if you're producing an OEM part for switching the lights on and off in a car, that might be an element that goes into multiple models, car models that is, and you might have a computer model of that. And FMI allows you to send that up the supply chain, get it tested with a simulation model, which is now a barrier or a hoop that those suppliers have to go through, because it saves the company so much time that they're able to test things in simulation before, let's say, shipping a new part all the way to another country, for example, and testing on a physical test bed. So that's really where FMI came from. The work I've been doing over the last few years with collaborators across Europe, funded by the European Commission, is to look at other domains where FMI could be used. Now it's been released by automotive and bringing that into other areas. One really interesting one that worked very well for a small company in Denmark is on precision agriculture. So this company had a background in building tractors, and they're really a traditional metal bashing 1940s, 50s tractor company that used to produce these quaint little tractors. Now tractors are huge machines with touch screens and comfy seats, which really mean that in order to keep up, they have to develop software. And that's something that they initially struggled with upskilling their company in. So they're using FMI to collaborate between the metal bashing producers of the physical hardware and the new software people coming in trying to build the controllers. And they now develop a smaller, lightweight, autonomous tractor. And the interesting thing about tractors is a lot of things are based on history. So there's a tradition of how far apart plants are planted, and that's based on the width of an ox. So farming's been done for thousands of years, and there are all these things that are built in based on the width of physical properties of animals, for example. Each farm is slightly different. So what they're able to use is use these models that are using FMI. A customer comes along and says, I'm interested in your autonomous farm vehicle, but I'd like to attach this old sprayer that I've got, which is a certain size, or my fields are this shape. And because they have a model, they're able to change different aspects, and the different departments can do the tweaking on their part of the model. But then the overall system is then simulated, and they're actually able to sell to a customer a bespoke, tweaked version of their autonomous farm vehicle. But they're able to test that without spending any particular money on building a product that check that it works. They're able to run a simulation with the customer, work out the customer's needs, check everything's okay, and only then commit to actually producing the hardware, which for a small company might be quite a large percentage of turnover if something falls through. And that's really where FMI has worked for them.
Thank you very much, Ken. That's covered some of what's already been achieved, but I believe you have dreams, plans, aspirations to take FMI to new places and achieve even greater results. Using railway examples, if you can, could you tell us what you think FMI might help us to achieve in the future?
Maybe I'll have a go at this. I think there's two major themes where we see benefits to FMI in the future. I think the first, as I alluded to earlier, is the opportunity to use FMI on the cloud. So at the moment, a lot of the implementation of FMI is using local or relatively local coordination of models and simulations. But what Ken is involved with, there's a whole program of work across the EU at the moment, is to understand how we can move modeling and simulation capabilities onto the cloud. Now, what that will allow you to do is to remotely, as a small supplier, as Ken described just now, is to put your model into a larger simulation context and see whether it works. Now, the advantage for the railways is this suddenly opens up a much richer supply chain. And we know for organizations that are outside of the rail sector, it can be really challenging and daunting for them to fit in and understand the ways of working and the kind of parameters that the rail industry works towards. Essentially, what we can do through the cloud is give them almost like a sandpit where they can try out their models and bring them in. Now, you think about stuff like batteries, say, or new types of, say, air conditioning subsystem and so on. What there may be is providers from other sectors, from the automotive sector or the marine sector, something like that. And they can now try out their innovation in a relatively low cost, relatively easy way. And what that opens up for the rail sector is a whole bunch of new suppliers who they'll be able to work with. I think the second vision that we have for taking FMI forward, and this is something particularly of relevance to me and of interest to me, Let's say I work in human factors. By background, I'm a psychologist. I think it's really key that we are able to represent and model human performance in a realistic way. I think there's real potential for FMI to allow us to build rigorous human performance models of, say, driver performance, or even things like signaler performance, which we then use in a multitude of different settings. And this has two benefits. First of all, we've now got some standalone rigorous model of what a driver is and different types of driver behavior. We can tune that over different parameters. How might drivers behave differently if they are fatigued, or if they've been through a training program that allows them to drive in a more driver efficient manner. But also the feedback from the rail sector allows me to fine tune those models so my models become more accurate over time, and I can start to incorporate real driver performance data into my simulation models. So there's a really nice feedback loop there. And what I hope is we're able to provide in time is really accurate human performance modeling.
Thank you, Dave. To finish off, I'd like to look to the future a bit more. The recent William Schaap's white paper on their vision for the Great British Railway to become far more cost efficient, far more sustainable, and deliver far greater customer satisfaction. What do you believe the FMI model might be able to deliver to make this a reality?
Perhaps I can go first and then Dave can come in with some of his views. I think looking forward, something like FMI, the railway industry might, for example, take a lead from the automotive industry. So previously I mentioned you've got large manufacturers who are mandating the use of FMI. So if something like a common standard is then suggested like FMI, then anyone trying to do work on the railway, filling in tenders, for example, could then be required to demonstrate the performance of their proposed solution using something like FMI. And this is seen also more in the built environment industry at the moment. We're now seeing much more building to performance. So you're not requiring the building needs to be this size, you're requiring that the CO2 footprint needs to be this small. And then it's up to the architects and other people to build a solution that meets those performance. And modeling is used there. So BIM, building information modeling, is used. And I believe FMI could be used in a similar way. If any tender is required to include a model that's FMI compliant that can then be tested on a system model as a co-simulation, for example, then we're much more able to say that those tenders are going to reach the potential and make a choice really based on the performance that is expected. And in a way, this can also lower barriers to entries for startups and SMEs, because we're taking something like FMI, which is under the surface a fairly simple thing to do. Then companies can come up with ideas, build models of them, and then compete with more established figures by using this sort of great leveler of the FMI model. And also we can imagine if collaboration became a regular feature of work in the rail industry, then FMI might be one of the key pillars underneath that. So if all modeling done in the industry is required to be FMI compliant, then between any of those industry aspects, we can always bring those models together and really look at the overall system.
Thank you very much, Ken. Dave, would you like to add anything else to that?
Really, just to say that, William Schaap's is there to prompt and deliver solutions to systems problems. It's about better, cheaper, faster delivery of new infrastructure. It's about operating better. It's about better capacity. It's about less disruption. And it's also about achieving net zero. Really, it comes down to it. They're all systems problems. And ultimately, FMI is an enabling capability that allows us to model and simulate to solve these kind of systems problems using all those advantages that Ken has just described.
Thank you very much, Dave. Thank you very much both for explaining to us something of both how FMI works and how it can and has been used in the railway already. I hope we're going to be able to produce some future episodes that look at specific modelling collaborations, and we'll have more details of those in the future. For now, everybody, thank you for listening this far, and if you have any questions about this or any other podcasts, please email me at podcasts@rssb.co.uk. In the meantime, thank you for listening and stay safe.